All right, we're on chapter 3, aerodynamic forces on airfoils. This shouldn't be too long of a lecture. I just want to go over a few important things here in this chapter. Specifically, let's go over some airfoil terminology. So let me draw an airfoil here. And if we label some components, this is going to be your chord line. This will be mean. Camber line. This distance here is your chord. Wherever the maximum thickness is of this is going to be your max thickness. It's pretty self-explanatory. And the difference or measurement between the mean camber line and the chord line is your max camber. And this is all depicted in figure 3.2 as well. If you look at figure 3.3 on page 32, you'll see a drawing for a symmetrical airfoil and a cambered airfoil. So symmetric, it's basically, as it says, symmetric. If we drew the chord line and we folded this, it would be the same on both sides. And if we drew a cambered airfoil, similar to what we just drew a little bit ago, it's basically not going to be symmetric if you fold both sides. All right, look at the definitions on page 33. I'm not going to go over all those, and there's some definitions on page 32 as well. So just take a look at those definitions. All right, we look at forces acting on an airfoil. This might be a little bit of a review for you, but we'll go ahead and draw this out because it is important to have these basic concepts. Relative wind, here's your chord line. This is angle of attack, which we refer to as alpha. Aerodynamic force. And we know we can break this up into lift and drag. And this is, again, the chord line. Okay, so this is showing the depiction of how forces occur on the airfoil. So your main things: lift, drag, aerodynamic force, and angle of attack, and we'll get to center of pressure and aerodynamic center here in a moment. Okay, I'm going to skip the depiction of flow over cylinder. I'm just going to jump because all it's doing is leading up to static pressure changes about an airfoil. So now we're on page 36 and in figure 3.7. So 3.7 showing two things, and this is an important concept. Figure 3.7a shows an airfoil at zero angle of attack, and 3.7b shows an airfoil at a positive angle of attack. So for a symmetric airfoil at zero angle of attack, what happens is the pressure distribution on the top and the bottom counteract, and therefore no lift develops. So as we know from Bernoulli in 3.7b, the airflow must speed up more as it passes over the top, resulting in a larger lower pressure area. So this is how we get lift to develop at a positive angle of attack. So most of your airfoils are going to be designed even when you're at straight and level, and this is an important concept because a lot of people think, well, at zero angle of attack, I'm generating lift because I'm flying. Well, you are, but it's inherently designed into the airplane. because the airfoil has been chosen for that airplane to still give you some lift at straight and level flight, which is counteracted by other forces in the airplane. But this is an important concept to understand because this can get a little confusing. But I think we all understand as we increase angle of attack, lift is going to increase. And that's what figure 3.7a and 3.7b is showing you. So make sure you understand that concept. That's an important concept to understand. All right, if we look at the aerodynamic force, and I'm not going to spend a lot of time on this, but just to go over it, it's more of a terminology thing. Again, the chord line, the center of pressure, which you call CP, is going to act with the aerodynamic force, which is broken into lift and drag. CP will changes with alpha, angle of attack. So center of pressure is going to move all along the airfoil as we change angle of attack. And you go back and look at 3.7b, that makes sense because that positive lift component, as I increase that angle of attack, that positive lift component is going to get bigger, and that center of pressure is going to change among that airfoil. If you look at page 38, what they're depicting here is a reverse cambered airfoil on 3.7a. So reverse cambered airfoil is basically going to look bigger at the bottom than the top. That's a really bad drawing, but I think you get the idea. Just look at 3.10, page 38. So we're on the same page. Figure 3.10a shows us the reverse cambered airfoil. And this is important in delta wing aircraft because delta wing aircraft are normally designed to be negative stability, increased maneuverability, and they have a tendency to have a downward nose attitude based on the airfoil we're picking in the design of the wing, being a delta wing. So we will pick airfoils that gives us a nose up pitching moment inherently designed into the airplane. And that's the purpose of reverse cambered airfoils. And then last we'll look at aerodynamic center. So if we draw an airfoil again, we say this is center of pressure. Aerodynamic center is going to be somewhere in front. And unlike center of pressure, aerodynamic center will not change with alpha. Okay? That's it for chapter 3. Pretty straightforward, just a few concepts to grasp here. The idea of reverse camber, symmetric and non-symmetric airfoils, and airfoil terminology and forces that act upon an airfoil. If you understand those components, you should be good to go on chapter 3. Thank you.